Dear colleagues, today I will present you my software, GeoSpring 1.0. So, this software was developed for the design of shallow and deep foundations, as you see. The development of such a product, it has started since 2015. So today we will see the futures of GeoSpring in the design of shallow and deep foundations. So let's go ahead. Basically, GeoSpring, it contains 4 modules. The first module, it's about the design of shallow and deep foundations. So it computes the bearing capacity and settlement. The second module, it's about pile foundations. So it computes the settlement of pilot foundations, single piles and group of piles also. The third module, it's about the design of rigid inclusions. And the final module, it's about the settlement of embankments. So the short-term and long-term settlement of embankments. So today we'll see the embankment section in GeoSpring 1.1. So how we compute the settlement of a given embankment using GeoSpring. So let us start. Actually, there is 2 methods: the short-term settlement and the audiometric settlement using compressibility parameters. So let us start about short-term settlement. So here you will have a window, you will just open it. You will insert the thickness of each layer beneath this embankment. For example, let us say here 7 and 7. Here you will insert the deformation models of each layer. 25, for example. 35. And here you will insert the height of the embankment, 7 meters for example, the density of the embankment itself, the material, and the A and B dimensions according to Osterberg dimensions. Actually, A, it's the half of the horizontal width, and B, it's the second horizontal dimension corresponding to the slope of the embankment. Let us say, for example, 5 and here 6. Okay. Here I forgot to tell you, here you have to put the Poisson ratio of each layer. For example, 0.33, 0.35 and 0.4 and 0.4. Okay. Okay, and just you have now, when you push the button, the distribution of the settlement along the embankment width. So it gives you the maximum value settlement in axis of embankment, and it also gives you the distribution of the settlement along the embankment width. Here it will be interesting such a numerical distribution to be used to optimize the design, for example, of a soil improvement alternative in this area close to the axis of embankment than in this area. Okay, so now let us move to estimate the odometer settlement. Okay, the long-term set or the total settlement of a given embankment according to odometer data. For example, 5, 5 and 5. 3 layers. Here you have the density of each layer. Okay, here you have the CR coefficient. For French code users, it will be CS and not CR. Okay, so 0.02, example, 0.015 and 0.01, 0.2, point, for example, 15 and 0.17, for example. Arbitrary values. Here you put, for example, 150, 190 and 200. Here you have the initial void ratio, 1.2, for example. Here 1.1. 1.2 and 1.9. Here you put the height of the embankment, the density of its material, water table 3 for example, and A and B 5 and 5. So after putting the odometer data and the geometry of the embankment and its material characteristics, you push the button here and you will have the variation of settlement along the embankment width, and also distribution will be useful to optimize a vertical drain solution to accelerate the consolidation of a clayey layer located below the embankment. So people say, if for example we have a sandy layer here and a clay layer here and a sandy layer here, you will just put in the sandy layer terms CR equals 0 and CC equals 0 to mention that these layers are not compressible. So that's it. Thank you very much, and see you in the rigid inclusion section.